Hello students, we're starting chapter 6, and the two important things to focus on in this first part is the use of curved arrows, double-headed arrows, and fishhook arrows. Also, the difference between polar reactions and radical reactions. Let's get started. I first want you to see the different types of organic reactions. So we're coming to an exciting time because we're finally getting to the heart of organic chemistry, and that's the different types of reactions. So this is just an overview. There are many specific examples. A substitution is substituting one group for another. Here, chloride will come in and kick out or replace the OH. There are a lot of conditions that will make this favorable. An addition across a double bond and even a triple bond can occur. And here you can see you could break the pi bond and attach two bromines. You can attach a lot of other different things. There's a whole chapter on alkene chemistry. Elimination, you could do the opposite. So here you could dehydrate, remove an H from here and an OH, and regenerate an alkene. Or you can do a rearrangement. I can protonate this OH to water. This can kick out, generate a carbocation, and this methyl group can move over, generating a more stable carbocation. There's always a driving force for chemical reactions, and generate this rearranged compound with a newly formed alkene. There are two types of arrows that you'll use. The double-headed arrow that shows the flow of electrons of 2 electrons, and the fishhook arrow, which applies when you're dealing with radicals. So most of the time you're just using this type, the normal arrow. I would say 95 to 99% of the time. When you're working with radical reactions, that involves the movement of a single electron, so use the fishhook. Here is how I break down two different types of reactions. And these show what are called the mechanisms, how reactions occur. The first is neutral, involving radicals. And this first is an example of what's called a homolytic cleavage. So the Cl-Cl bond in chlorine is made of 2 electrons. What can happen if initiated by heat, given this delta sign, or light, H nu, you can break this bond, and what can happen is 1 electron will go to each chlorine to give these radical species. You can also show it without the exterior lone pairs. But basically, look at this chlorine. There's no charge. This is its normal valence of having 7 electrons around it. 2 electrons can join, 1 each from a radical, and look at the fishhook arrows. They're joining kind of in the space between them, and that will result in a single bond. The other type of main reaction is a polar reaction. This is the majority of what you'll see. Here's a substitution. I'm going to start with NH2 minus, a very strong negative charge, and that lone pair is going to go to attack the C. The reason is that C is partial positive because of the electron withdrawing chlorine. But it can't just stay there because carbon can only have 4 bonds. So this bond between carbon and chlorine has to break, and the 2 electrons in that bond go up as another lone pair on chlorine. Chlorine gets a negative formal charge. So here we have lone pair to form a bond, and then here the bond is then breaking to become a lone pair. Just a bit on radical reactions before I move to polar. There are 3 steps in a radical reaction, and we'll look more at this later, but this is important chemistry for polymer synthesis and certain biochemical processes. The first step is initiation. I already showed this using light or heat. Propagation, where you get the radicals to react, but then that propagation generates a new radical to continue the chain. And then termination, any 2 radicals will react to form a stable molecule that ends the chain. Let's look at this example. Here's initiation with heat or light. I'm going to break the Cl-Cl bond to form two Cl radicals. That's it. Propagation. The chlorine can react with a neutral methane. And again, look how the fishhook arrows are moving. You will be expected to do this on your own. When you do a fishhook arrow here, that means only one electron in the CH bond will move and join with this chlorine radical to form an HCl bond shown here on the right. But what happens to the other electron? Look at follow the fishhook arrow. It goes and remains on the carbon. So you generate a methyl radical. That's what continues the chain. This methyl radical can then react with another neutral molecule here with chlorine. So this is just an example. And you can form a CCl bond shown here, generating chloromethane and regenerating a chlorine radical, which can keep the chain going. So overall, methane plus chlorine under radical conditions, heat or light, will generate a monochloromethane. Very powerful way to chlorinate or brominate, for example, alkanes. The termination step is any two radicals joining to form a neutral molecule. Eventually, this stops the chain reaction. Now on to polar reactions. At the core, plus is attracted to minus, a positive end is attracted to a negative end, vice versa. We've seen this as the basis for covalent and ionic bonding. This is also the basis for polar reactions. Nucleophiles, these are the species that have a full or partial negative charge, are attracted to electrophiles that have a positive charge. For example, B minus here is a nucleophile, which means nuclei loving. It loves the positive nucleus of another, it's attracted, so it'll go and attack and form a bond with an electrophile. And an electrophile is electron loving. So it means it's deficient, it wants electron density. So it's a match made in heaven. They become a couple. You want to visualize this. Eventually, you guys are just going to be given certain molecules, and you knowing polarity, knowing the dipole direction, knowing resonance structures, will be able to predict where certain molecules are going to react. For example, methanol, it has a partial positive C and partial negative O. So if a nucleophile comes in, it'll attack at the carbon center. Another thing to note is this can be acidic depending on what's available. So it's possible a strong base can come in and grab that H+. So differences in electronegativities give rise to what's positive and negative here, partial positive and negative. So O is more electronegative than C. That's how I knew this. Keep in mind that you can have a metal attached to carbon as well. And so in that case, the carbon is more electronegative than, say, lithium. And that means there's more electron density in the carbon. So then in this case, the carbon or methyl lithium is electron rich and becomes the nucleophile. So this all depends on what the atoms are attached to. There are very, very common patterns that you're going to see with certain functional groups. So look at this. An alkene is symmetric, it's nonpolar, so that can act as a nucleophile. Depending on what's near it, it can also act as an electrophile. But if you have a carbon next to an electronegative element, like I show all here, you're going to have a partial positive C that will want to be attacked by a nucleophile. There are special cases where the carbon is attached to a metal, and in those cases, the carbon is nucleophilic. It'll act as a nucleophile. This whole right side are carbonyl compounds. You guys can draw a resonance structure where the pi bond here can become a lone pair on oxygen, and the carbon is a carbocation. Overall, the hybrid is shown here, Anything with a carbonyl will have a partial positive C. So a lot of reactions will attack at the carbon. Okay, that ends this section. Next time we're going to be looking at more specifically the energy diagrams. I'll see you guys next time.